Hello, everyone. I'm pleased to see you all here. So this is a Bitcoin crash course. It's going to be a bit of high pace, but I'm trying to do this as simple as possible. And this course is about Bitcoin and how Bitcoin can achieve censorship resistance. So how can we create censorship resistant money? Because that's what Bitcoin is all about, censorship resistance. And this is about me. I'm Kalle Rosenbaum. You can reach out on Twitter to me at Kalle Rosenbaum and on Mastodon. You will also have my email there. And my ICQ number is 355025, but don't use that. I haven't used it for 20 years or so. And my PGP fingerprint is here as well if you want to communicate in private with me. And I want to say a few words about the course material. The course materials is grokking Bitcoin, and I wrote this book a few years ago, and it's been out for 2 years. And I find the book pretty good to have as a base for this course because it builds Bitcoin from scratch. I will talk a bit more on that later. But if you haven't downloaded it yet, I recommend that you do. First of all, you can browse the book for free on this URL on top here. But that's the online version. I suggest that you instead go to this URL at the bottom here, rosenbaum.se/book/grokkingbitcoin.tar.gz, and download the book in full and browse it locally on your computer instead, because that would save bandwidth both for me and for you. And this book is, of course, if you want it on paper, it's a little late now, but it's available on online bookstores, and the ebook is also available at manning.com. But I recommend that you just download this open source version of the book and use that. It's the exact same content as the commercial book, if you will. So what we're going to do is build Bitcoin from scratch. And we are going to start with a really stupid money system that I call cookie tokens. And I do this because I want to start at a point where everybody can understand this base system. Yeah, so cookie tokens is bad in lots of regards, but it's very, very simple. So, and from there we will, chapter by chapter, we will add new technology. We will point out a problem with the current system, and we will fix that problem with some Bitcoin technology. And towards chapter 8, we will have built Bitcoin in full. And from there on, we will only talk about Bitcoin. We will leave the cookie tokens there. So yeah, so at chapter 8, we have achieved Bitcoin, which is censorship resistant money. And then we will have some labs where we set up our own Bitcoin full node so that you yourselves can verify all the transactions in the Bitcoin network and all the blocks, so that you don't have to trust someone else with that. And we will also send some test coins between each other. Today, we are going through chapters 2 to 4. I think we can do more chapters today than the other days because it's a bit simpler this first day. So we're going to talk about cryptographic hash functions and digital signatures today. And we're going to use that knowledge to create Bitcoin addresses and wallets. And Tuesday is going to be about transactions and the blockchain, and Wednesday, proof of work, peer-to-peer network. Thursday is going to be about segregated witness, which is an upgrade to Bitcoin that came in 2017. And we're also going to talk about how to upgrade Bitcoin with soft forks. as you may have noticed, I have skipped chapter 9. And I encourage you to read chapter 9 after chapter 8, but it's not mandatory. I took out chapter 9 in order to make room for the labs. Okay, so I already told you that we are going to start up with a very silly, stupid money system that I called cookie tokens. So you have to imagine an office, for example, where you have a cafe in the office and you have people who want to buy stuff in this cafe. For this, you use something called cookie tokens. And this is an online spreadsheet that everyone has access to. So everyone can read this spreadsheet. And there's one person who has right access to this spreadsheet, and her name is Lisa. She's the central authority of this system. She's the one adding new payments to this spreadsheet. So if, as you can see here, you have 3 columns: from, to, and amount. And if you look at this row, the first row here, Alice sends 10 cookie tokens to the cafe, and then to buy a cookie. But you can use this for anything. You don't have to buy cookies. You can do them to settle debt or buy bicycles or anything. So when suppose now that Alice wants to buy a cookie at the cafe, what does she do? Yeah, she goes to Lisa and say, "Hi Lisa, please transfer 10 cookie tokens to the cafe for me, please." And Lisa, she knows Alice's face. She knows who she is and can verify that, okay, this is Alice. So I'm going to search for Alice in this spreadsheet to get all the Alice's transactions where she's involved. And she can see here that Alice has 1 incoming payment for 100 cookie tokens and 2 outgoing for a total of 30 cookie tokens. So she has 70 cookie tokens. So she has the money to spend. She has 10 cookie tokens to spend for a cookie, which is nice. And so Lisa will gladly now add a new row to this spreadsheet, Alice Cafe 10. And the cafe will see this new payment in the spreadsheet because everyone has read access to this spreadsheet. So when the cafe sees this row here, it's gonna hand out the cookie to Alice, and Alice can eat it. So that's the very basic, simple system that we start out with. Oh, one more thing. Everyone thinks that Lisa is doing a good job. She's securing this system very well, and she's thorough and trustworthy. So everybody likes her work and appreciates it. They value her work. So they have agreed that every day Lisa is allowed to add 7,200 new cookie tokens to herself with newly created coins. So this payment is not from anyone in particular. It's a payment from newly created coins. So the total amount of coins is growing, which is the money supply. So it's growing currently by 7,200 cookie tokens per day. So that averages to 50 cookie tokens each 10 minutes, if that's familiar to you some way. Okay, so Lisa is rewarded for her valuable work to secure this money system. But there's one more thing with this. When this reward to Lisa is not forever, because every 4 years this reward will be halved. So next time after 4 years, this will be halved to 3,600 cookie tokens, and so on, so that the money supply will look like this. The money supply will approach 21 million, because the first 4 years, half of the supply, half of the total supply will be created, and the next 4 years, half of the remaining half will be created, and so on. So that means that we're converging towards 21 million cookie tokens. So this is the same curve as we have in Bitcoin. So this is also Bitcoin's supply curve. It will never exceed 21 million, but it will increase towards 21 millions. Okay, so as you probably have identified already, there are several flaws with this system. I will name one specific such flaw, and that is someone can pretend to be Alice. And Lisa might not know everyone's face as the company grows. So Lisa is having a hard time keeping track of who's who, and she doesn't recognize everyone's face. So Lisa is going to start everyone to require everyone to provide a digital signature with their payments. And I'm going to show you how that works. But first, we need some basics. We need to understand the concept of a cryptographic hash function, and we need to understand digital signatures. And these two are like the atoms of Bitcoin. If you understand these two concepts, cryptographic hash functions in particular, and digital signatures, you are in a good position to actually understand Bitcoin. So cryptographic hash functions are used everywhere in Bitcoin. So let's start with a cryptographic hash function. A cryptographic hash function is a function that takes a single input and has a single output. The input is anything. It can be a picture of a cat, or it can be my entire music collection, or it can be the string hello. And there is no size requirements. It can be as big as you want and as small as you want. And the output is a fixed size number, which we call a hash. And it's important to realize also that a cryptographic hash function cannot be run backwards. If you have the hash, it's really hard to find an input that has that hash as its output. So you can't move backwards through this cryptographic hash function. Now, and also another important aspect is that if you change the input the slightest, you will get a totally different output. So, for example, if you look at the bottom of the screen here, we have removed a single whisker from this cat picture. So there's a tiny change in this cat picture, but as you see on the output is totally different than the previous output. So a tiny change in the input will cause a huge change in the output. So the output will look like random numbers, huge random numbers. I will reiterate this in this picture. So we have four general big properties of cryptographic hash functions. The first one is that if you input the same input will give you the same hash, the exact same hash every time you input it. That's pretty natural, but that's important. And if you change the input slightly, you will change the output a lot, like it will be a totally different value. But it's also of the same size. It's also always the same number of bits that is output. For SHA-256, which is the most commonly used hash function in Bitcoin, it's 256 bits. So that's these are the first three important properties. And then we have the fourth property, which is pre-image resistance. Pre-image resistance is actually there are three categories of this, but let's start with the one in the middle, which is pre-image resistance. And that means that if you have a hash, it's really hard to figure out an input that matches that hash. The only known way to do this is trial and error. Just try an input and see what output you get until you have a matching output. And as you may guess, that's just not doable for this kind of cryptographic hash functions with 256 bits output. And we have some variations of this as well. We have on your left, you have something called collision resistance. And that means it's really hard to find two different inputs that will give you the same output, regardless of what output. So the problem here is to find two inputs that give two different inputs that give you the same output. And on your right, you have something called second pre-image resistance. And that is, if given a certain input, find another different input that gives the same output as the first one. So all of these are extremely important, and they are similar, but think of it all as just pre-image resistance. It's really hard to find an input that matches an output. And I think, yeah, so what is this good for then? It's good for integrity checks. Suppose that you have a cat picture and you want to save that cat picture on a hard drive, and then at some point in the future, you may want to read this cat picture again. And then you want to make sure that it's the same cat picture as the one you saved, so that it hasn't been tampered with, or yeah. So you save the cat picture to your hard drive, and you hash it through a cryptographic hash function, and you write the result on a piece of paper. And you take this paper and you put it away in a drawer in a safe place. And then 10 years later, you want to read this cat again from your hard drive, but you want to make sure that it hasn't been tampered with. It could be corrupted by hardware failures, or by some malicious attack, or by you accidentally editing it or destroying it. Either way, you want to verify that this is the same cat. And suppose that it has been tampered with. Someone has been here and removed this whisker. So you read the cat picture. Now it's 10 years later. You read the cat picture from your hard drive, and you run it through a cryptographic hash function, and you get the hash, the actual hash of the cat picture. And then you compare that to the one you have in your drawer on the piece of paper from 10 years ago. And since the cat picture has changed, you will get a totally different hash, and the comparison here will fail miserably. So then you will know that something has happened to this cat picture. You don't know what, you don't know when, and you don't know by whom. You just know that it's changed. So this is useful as an integrity check on data. So to summarize cryptographic hash functions, a cryptographic hash function has an input and it has an output. And the input can be anything, and the output is a fixed size number. For SHA-256, it's a 256-bit number, which is a huge number. And I usually draw cryptographic hash functions like a shredder like this, and the cryptographic hash will be a pile of paper. So I like pictures. I don't know about you, but I like pictures, and so I use pictures a lot. And all pictures you see in this presentation is from my book. So you will have the same pictures in the book, and you will recognize them from there. Okay, so this was cryptographic hash functions.